So we ended. It's 2. So we ended last week with looking at Havel Hakimi, and I'm going to prove Havel Hakimi, but I want to do. I want you to do 2 more degree sequences. Are these realizable? So take a minute. And of course, the first thing you should be checking, if they have any chance of being realizable, the sum of the degrees should be even. So class has gotten smaller. Ying, is that my fault? No? These are 2 questions, right. It's not one long degree sequence. This is 2 different questions. So you got no and yes. Okay. Well, anybody? Which one does one work and one not? Yes. That's true. Which one do you think works? This is a yes, and this is a no. So what happened when you tried to do the top sequence? So Havel Hakimi says. Everybody's done with that. Okay, so Havel Hakimi says that if it's realizable, then and there are many realizations. Okay, the one thing that we'll talk a lot about. Just because we have a degree sequence, there can be many realizations with that degree sequence. Okay, so this is not the only one. But Havel Hakimi tells us that if there's a degree, if this is realizable, Then there's a realization where the vertex of highest degree, this is a vertex of highest degree, is adjacent to the next D1 vertices of highest degree. And I'm going to prove that in a minute, vertices of highest degree. I mean, essentially, that's what Havel Hakimi says. And by actually proving this, this gives us an algorithm, a set way to actually determine whether a certain degree sequence is realizable. And what's better than the other condition given in the book, the Erdős-Galai condition, which is just a bunch of summations. You check a bunch of summations for the Erdős-Galai, and it says, it pops out either yes or no. But you don't know what the realization is. In Havel Hakimi, you'll get a realization of the original degree sequence. Okay? So that's the important part of Havel Hakimi, is you'll be able to actually go backwards with the algorithm and construct a graph. In this case, if this is a no, then you won't be able to construct it. If the second one was a yes, then we'll be able to construct it. Okay, so what happened with 87665332221? So what's the first step that you? We take away the 8, and we subtract 1 from the next 8 degrees. So we have 6, 5, 5, 4, 2, 1, 1, 1. Let's see, how many is that? 1, 2, 3, 4, 5, 6, 7, 8. So that's 3 2s and a 1. So that would be the degree sequence. That would be the next degree sequence. So again, if this is realizable, then this is realizable. And if this is realizable, then 4, 4, 3, 1, 0, 0, 1, 1 is realizable. Oh, we have to keep them ordered. So I'm going to rewrite this as 4, 4, 3, 1, 1, 1, 0, 0. So again, if this is realizable, this is the same degree sequence. So if this is realizable, then 3, 2, 0, 0. 3, 2, 0, 0, 1, 0, 0 is realizable. Ordering them up again, 3, 2, 1, 0, 0, 0, 0. Of course, the zeros, that doesn't give you much. But now I only have 3 vertices with positive degree. And as a graph, not a multigraph, 3, 2, 1, 0, 0, 0, 0. Of course, the 4 zeros are here, and we have 2 more vertices. There's no way of degree 3 in a graph without having a multiple edge. Okay, so this is not realizable as a graph, and the second one was realizable. And the nice thing about it is, once you get to that point where you know there's a realization, you can actually build up to a realization of the original degree sequence. Okay, so why does this work? So so now I'm going to prove Havel Hakimi. Okay, so what it says is I'm going to take the vertex of highest degree, and let's imagine that I have a vertex of highest degree D1. And I have a realization, and I look at the vertices of the vertices that are adjacent to the vertex of degree 1. This is a vertex of highest degree. Okay, so one more time, let me repeat what I'm actually proving here. So if there's a realization, and there may be many realizations, can you give me a degree sequence that has more than one realization? Don't think too hard. How about 6 2s? Can you give me a different realization of the degree sequence with 6 2s? two triangles. Okay, so there are actually many realizations, not just one or two or seven. There might be many realizations of a particular degree sequence. Okay, but what Havel Hakimi says is, if there's a realization, then there's a realization where the vertex of highest degree is adjacent to the D1 vertices, the next D1 vertices of highest degree. Right, that's what we did here. So we took the vertex of highest degree, 8, and we subtracted 1 from the next 8 numbers. So if I was going to build this up, this vertex of degree 8 would be adjacent to the next 8 vertices of highest degree. Okay, so that's the power in what Havel Hakimi says. Okay, so we have a realization. So the degree sequence is realizable. And I look at a realization, and D1 is the vertex of highest degree. D1 is a vertex of highest degree. So we have, let's see, it's adjacent to x1, x2, x3, x D1. Now, I don't know what this realization is. If x1, x2, x3 up to xd1 are vertices of the next highest d1 degrees, then we'd be done. If the degrees of x1, x2 up to xd1 were the next highest degrees, then we'd be done. If that was the case. So suppose these aren't the next highest degrees. Suppose there's a vertex, and this is just a piece of the graph, right? So there's a typical picture that I might have in a proof of a graph theory problem that I'm trying to prove. If there's a vertex here, let's say, let's call this y. So that the degree of y, green's not too good. So the degree of y is greater than one of the degrees over here. So this vertex of highest degree is not adjacent to one of the next vertices of highest degree. So let's assume the degree of y is strictly greater than, let's say, the degree, just for geometry, let's just say the degree of x1. Now, what I would like to do, now this is the realization of this degree sequence. So this means that this vertex here is not adjacent to y. And the degree of y is greater than, the degree of y is greater than the degree of x1. It's greater than the degree of this vertex here. So there is a vertex z that's adjacent to y that's not adjacent to x1. One more time. The degree of y is greater than the degree of x1. So there is a vertex z that's adjacent to y that's not adjacent to x1. Is that clear? Everybody with me? Because now I'm going to say this word, and you're never allowed to use this word. Now the magic happens. Okay? Wait a minute. What do you mean magic? Okay. Now let's look at these four vertices. These four vertices. This vertex, why is the vertex I'd like D1 to be adjacent to? Y's got higher degree than x1. Y's degree is higher than the degree of x1. So I would like this vertex to be adjacent to y rather than x. Okay? So what I'm going to do is, remember, this is just one realization. This is one realization. And there are many realizations of a particular degree sequence, and we'll see that in a second. So what I'm going to do is I'm going to change this realization to a different realization. You can almost see what's going to happen. I'm going to put D1 adjacent to y. I'm going to take this edge out, put this edge in, and take this edge out. Okay, is that clear what I've done? Let's make sure the degrees are okay. What happened to this vertex up here? I added an edge, and I took out an edge. What happened to this vertex here? I added an edge and took out an edge. This vertex here, I added an edge and took out an edge. And this vertex here, I added an edge and I took out an edge. Okay, so I've replaced two edges with two edges. So what's the degree sequence of this new graph? What's the degree of x1? Let me start up. What's the degree of this vertex here? Same D1. What's the degree of y? Same thing. Degree of z, and the degree of x1. It's the same degree that I had before. I'm removing an edge and adding an edge. So everybody's degree is the same. And look what's happened. Now I've put this vertex here adjacent to the next highest degrees. So this is really the key, that the vertex of highest degree this is the key to Havel Hakimi. The vertex of highest degree can be adjacent to the next D1 vertices of highest degree. And that's the idea that lets us proceed with this algorithm. That's what lets us do this. Okay, so what was that second degree sequence I gave you? Did I give you a second degree sequence? Yeah. 6, 5, 5, 4. 6, 5, 5, 4, something. 3, 3. 3, 3, 2, 2, 2. Okay, and before you even start this, I know you're tired of hearing this. The first thing I'm going to do is make sure that the sum is even. And even before I do that, I'm not good at addition. What I want to do is make sure that I have an even number of odds. If you have an even number of odds, an even number of odd numbers, then the sum is going to be even. Because I got an even number of odds, that's even, and then I'm going to add a bunch of evens. So do I have an even number of odds? 5, 5, 3, 3. So I have 4 odds. So is this realizable? Well, it better be. Yeah? Everybody got a realization? And they don't have to be the same realization. As we'll see, that these realizations can be different. So here's my vertex of degree 6. Well, let's work backwards. It's easiest if I work backwards. So if this is realizable, then 4, 4, 3, 2, 2, 2, 2, 2 is realizable. Nope, sorry. Not enough. 1. One more time. Take away 1, 2, 3, 4, 5, 6. Now, it's important. You have to reorder it. Maybe it's not important here, but first thing I'm going to do is reorder this. 4, 4, 3, 2, 2, 2, 2, 1. The vertex of highest, if this is realizable, the vertex of highest degree is adjacent to the next highest degree, next, in this case, 4 highest degree vertices. So if this is realizable, then 3, 2, 1, 1, 2, 2, 1 is realizable. Order it. 3, 2, 2, 2, 1, 1, 1. By the way, at any point, if you see the realization, you're done. And you might you might actually try this just for the heck of it. Oh. There's a realization of 3, 2, 2, 2, 1, 1, 1. Okay, but if I didn't see that, I would continue. So the vertex of degree 3 is going to be adjacent to the next highest ones. So next I'm left with 1, 1, 1, 1, 1, 1. That's not a 1 here. No, that is a 1. Let's try that again. 1, 1, 1, 1, 1, 1. 1, 1, 1, 1, 1, 1. So working backwards, of course, hopefully you see that this is realizable. I mean, you could continue. The vertex of degree 1 would have to be adjacent to a vertex of degree 1. And then these would be zeros. Then the 1 would have to be adjacent to the 1. And then the 1 would have to be adjacent to the 1. So that's this degree sequence here. And now the 3 has to go to 3 of the 1s. So 3 of the 1s, vertex of degree 3, has to go to 3 of the 1s. By the way, it's not unique, right? The vertex of degree 3, has to go to 3 vertices of degree 1, so that's another graph that attains 3, 2, 2, 2, 1, 1, 1. So it's not a unique realization. And then you continue. Okay? Continue until we get 6, 5, 5, 4, 3, 3, 2, 2, 2. Questions? Questions about that? Okay, so it's now past 2 o'clock, and if you're looking at Canvas, I think homework became available at 2:01. Became available at 2. I want to talk about 7, 8, and 9. Now, there's no, I mean, really what I want you to do is think about how you would construct these graphs. Okay, so once again, I'm looking at page 89, 7, 8, and 9. And by the way, number 10 is on your homework. The homework is due next Tuesday. Maybe these aren't really. This is on page. At least in my book, it's on page 89. Yeah, yeah. 7, 8, 9 on page 89. So I know we only have Havel Hakimi at this point. So these questions are making you think about how we would construct new graphs, at least graphs with new degree sequences. Where did I get this vertex here? Okay, so what I know is y has some vertex. This vertex of highest degree is not adjacent to the next highest degree vertex. Suppose we have a realization. I would like the realization to be adjacent to the next D1 vertices of highest degree. Yeah. So I have a realization, and that's not the case. So this is a vertex that doesn't have one of the next D1 highest degrees. Okay, this vertex has degree higher than x1. One more time, degree of y is greater than the degree of x1. Okay, we know that, and we would like y to be one of these. It's one of the good ones. Okay, so I want to show that there's a different realization where the vertex of highest degree is adjacent to y and not adjacent to x1. Okay, so what I know is the degree of y is greater than the degree of x1. Strictly greater than. Strictly greater than. Okay, so there's a vertex z adjacent to y that's not adjacent to x1. One more time. The degree of y is strictly greater than the degree of x1. So y is adjacent to more vertices than x1. Okay?
What if there's another vertex and vertex w adjacent to y and z is adjacent to x1?
That's okay. I mean, so we can have. I mean, that's okay. But I just know that the degree of y, the number of vertices adjacent to y, is strictly greater than the number of vertices adjacent to x1. So I look at all the adjacencies of y. Some one of those points, maybe many of the points, maybe all of the points. Some vertex adjacent to y is not adjacent to x1. Because its degree is less than y. Okay, one more time. Some vertex z is adjacent to y, and it's not adjacent to x1. Okay, and now what I'm going to do is I'm going to look at these 4 points. So, and remember, there are many realizations of this degree sequence. We're not changing the degree sequence at all. We're just changing some of the edges. The degree sequence stays the same. So I know that this is not there. This is an edge. This is not an edge. And this is an edge. So let me draw this over here. Here's D1. Here's X1. Here's W. Here's Y. And I know that, I know that there is a vertex W adjacent to Y that's not adjacent to X1 because his degree is bigger than him. Okay, so there's a vertex W that's adjacent to Y that's not adjacent to X1. Now what I'm going to do is I'm going to look at those 4 points. I'm going to look at those 4 points, and I'm going to switch this out. So it's called an edge swap. So I'm going to swap this non-edge, and I'm going to put that edge in. I'm going to put this edge in. And where I had edges before, I'm going to put non-edges. So what happened to the degree of D1? we had an edge and a non-edge, and now we have an edge and a non-edge. X1 had an edge and a non-edge, and now it has an edge and a non-edge. W had an edge and a non-edge, and now it has an edge and a non-edge. And Y had a non-edge and an edge, and now it has an edge and a non-edge. So what we get is that now D1 is adjacent to more of the highest degree vertices. So we can continue to do that until this vertex of highest degree is adjacent to all the vertices of the next highest degree. Okay? That's the proof. Okay? Okay, so what about 7, 8, 9? What about 7? So let D1 through Dn be a graphic sequence. So what all that says is that there's a graph. I'm running out. There's a graph G. Here's a graph G. With x1, x2, up to xn, so that the degree of x1 is equal to d1, the degree of x2 is equal to d2. It's realizable. There is such a graph. Okay? So that's a graphic sequence. There is a graph. Now I'm going to look at, now read this carefully, d1 plus 1, wrong one, 2d1, d2, d2, d3, d3, dn, dn. So first of all, how many vertices is there? How many vertices did I start with? The first degree sequence has n, and the second degree sequence has 2n minus 1. Okay. So, any ideas? Here's a vertex of degree 1. In one copy, this is a graph that has degree sequence d1, d2, up to dn. Okay? So how many vertices are here, by the way? Let's count how many. I got one vertex has degree 2d1. And then I got 2 d2s, 2 d3s, 2 d4s, 2 dn's. How many vertices is that? 2n minus 1. How many vertices do I have here? N. This is n. So here's d1, and then I got a d2, d3, up to dn. Okay? What if I take another one? So here's another copy of this graph, G, and here's another copy. So what's the degree sequence of this graph? What's the degree sequence? Does everybody see the graph that, I know it's not much of a graph. I'm going to take 2 copies of G. 2 copies of G. First of all, how many vertices are there in 2 copies of G? 2n. And what's the degree sequence? Anybody?
Basically the same, duplicate.
But doubles. Yeah. I have 2 d1s and 2 d2s and 2 d3s and 2 d4s and 2 dn's. Now the degree sequence I want, how long is the degree sequence that I want? I have the first one, forget what the first one is. I have 2 d2s, 2 d3s, 2 d4s, and 2 dn's. Right? Okay, and what's the first degree? In your degree sequence. In the degree sequence of the problem given. The largest degree, I believe. in number 7, we have a vertex of degree 2d1. Then 2d2s, 2d3s, 2dn's. Okay, so how am I going to get a vertex? I have 2d1s and 2d2s and 2d. This graph here, if I just take the disjoint union, I have 2d1s, 2d2s, 2d3s, and 2dn's. I don't want 2d1s. So rather than having 2 of these vertices, I'm going to make a super vertex. And this super vertex, I'm going to throw away is not a technical term. I'm going to remove this vertex of degree d1. Now I don't want to change any of the degrees up here. So I'm going to put this vertex adjacent to the neighborhood of this vertex. So how many edges am I going to put in so far? Why d1, d minus 1? Well, d1's not adjacent to itself. I'm removing d1. What's the degree of this vertex here? 0. No. Originally. d1. So I'm going to remove this vertex and put this vertex adjacent to all the vertices that this was adjacent to. So the degree of the blue degree at this point is d1. Oh, but I'll do it here too. So I removed the edge from this point to these vertices here, and I've added this edge in. I've removed the edges from this point here to these points here, and I've added this edge in. So what's the degree sequence? What's the degree of this vertex? 2d1. And what's the degrees of all these vertices? All these vertices up here. They're the same. d2, d3, dn. And the degrees of these vertices here? Same thing. d2, d3, dn. So what's the degree sequence? 2d1, d2, d2, d3, d3, d4, d4, dn, dn. So the degree sequence is precisely 2d1, then 2 d2s, 2 d3s, and 2 dn's. Okay? Is that clear? Okay, and we're gonna be looking eventually at constructing graphs from smaller graphs. And this is one of the techniques, although this is pretty straightforward. Okay, what about the next one? And what's important is we have this statement, d1, d2 up to dn is a graphic sequence. So I know that d1, d2 up to dn can be realized as a graph. So now look at the degree sequence in number 8. By? Oh, I mean, I could, yeah, okay, so you want words. Okay, so let's try and write this with words. And this is great practice to write this with words. Do we understand how we're going to prove it? Okay, so let G1 be a graph with degree sequence d1, d2, dn, and greater than or greater than or equal to greater than. Okay? Okay, G1 is a graph with, okay? Then note, let x have degree, let the degree of x equal d1. Okay, so I'm gonna pick a, I know there has to be a vertex of degree d1 in there. Let's call it x. Okay. So what I'm going to do is now I'm going to look at x. Sorry. Okay, let G2 be a graph with the same degree sequence, except not x's, y's, with y1, y2, yn, where the degree of y1 is d1. Okay? So I'm gonna draw a picture, and then I'll write the words. So here's my picture. I have x has degree d1, y has degree d1, and this is a graph. This is, let's call this G1, and this is G2. Okay? So let's take it step by step. What can you tell me about the degree sequence? What's the degree sequence of G1 union G2? What's the degree sequence? And when I put union, I mean the disjoint union. Do I? No. So the degrees. So the degrees here are d1 through dn. The degrees here are d1 through dn. So the degree sequence of G1 union G2, union being they're just disjoint union. Then the degrees are d1 d1, d2 d2, d3 d3, dn dn is the degree sequence of this disjoint union. Ying? Okay? All right. Now form a new graph from G1 and G2. Take G1 minus x, G2 minus y. Consider G1 minus x and G2 minus y, and now form a new graph. Take that union and add a vertex z, where z is adjacent to the neighborhood of z is equal to the neighborhood of x in G1, union the neighborhood of y in G2. Okay, so one more time, I'm going to form a new graph. I'm going to take away x and y. So I'm going to take away x and y, G1 minus x, and G2 minus y. And then I'm going to make like a super point. And I'm going to put that super point adjacent to all the vertices adjacent to x, and all the vertices adjacent to y. So z, the neighborhood of z, is the neighbors of x in G1 and the neighbors of neighbors of y in G2. Okay, so what's the result? So the result is, now what's the degree of this super vertex? What do we call the super vertex? The degree of z is equal to what? Well, it was d1 up here and d1 up here. Sorry, d1 up here and d1 down here. So what's the degree of this super vertex z? d1 plus d1. Okay, so the degree of z is 2 d1. Okay? Well, what's the degree of every other vertex in here? No, not 2. So the vertex that had degree d2 now has degree d2. The vertex that had degree d3 now has degree d3, d4, d5, d6, and so forth. And the same thing goes here. So the degrees are so 2d1, and then 2d1, and then d2 and d2. There's a d2 up here, and a D2 up here, down there. Then a D3 and a D3. Right? There's a vertex of degree D3 up here, and a vertex of degree D3 up here. And finally, D and D. So my degree sequence is 2D1. Now I'm going to say this carefully. 2D1, and then D2, D2, D3, D3, D4, D4, DN, DN. Okay, I might have said it as 2D1, and then 2 D2s, and then 2 D3s, and 2 D4s. I'm not adding these up. So one more time. One vertex has high degree, 2 times D1, and then 2 D2s, and then 2 D3s, and so forth. I'm not sure you believe me. Okay, what about let's move on and see what we can do with the next one. Let D1 through Dn be a graphic sequence. And again, when you think of a graphic sequence, that means that there is a graph that has exactly this degree sequence. Show that the sequence D1 plus 1, D1 plus 1, D2 plus 2, sorry, D1 plus 1, D1 plus 1, D2 plus 1, D2 plus 1, Dn plus 1, Dn plus 1. So if the original degree sequence is realizable, this new degree sequence is realizable. And this is not unique. There's many ways to do this. So let's see if I understand graph theory is it's so easy to sometimes use a picture. But here's my graph G. Ying, you still?
No, we're working on the 8.
Oh, you're working on 8. Okay. So let me help you with 8. So what's the degree sequence? What degree sequence do I have? D1, D2, D3, Dn. So I know that's realizable. That's the assumption. That's realizable. I can realize a graph with that degree sequence. I can realize another copy of that graph. And maybe these are labeled x1 through xn. These are labeled y1 through yn. Here's another copy. Another copy of G. So the degrees of these vertices is D1, D2, D3, Dn. Now, at this point, let's look at the union, this union. What's the degree sequence of this graph here? What's the degree sequence of this graph as I drew it here? Yeah? Okay, one more time. D1, D1, D2, D2, D3, D3, D4, 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 Dn, Dn. Okay, that's the degree sequence. But that's not what they're asking for. What are they asking for? They want D1 plus 1 and D1 plus 1. Now, what's the degree of the top vertex? What's the degree of this vertex? This vertex? Okay. But I need, what's next? What else do I need in that degree sequence? Now, what's the degree of that vertex? Okay. Okay, and I'm only going to say this is not unique, right? I could be crazy, not crazy, but right. There's no reason why these are not totally disjoint graphs. I could have just put this one adjacent here, and this one adjacent here, and this one adjacent here, and this one adjacent somewhere over there. So I could have put any collection of edges that attached that adjoined the vertices in the top set to all the different vertices in the bottom set. And the degree sequence would still be d1 plus 1, d1 plus 1, d2 plus 1, d2 plus 1, dn plus 1, dn plus 1. Okay, again, we're just trying to give you practice at constructing interesting graphs. So now you kind of get the gist of this. What about 9? Okay, so d1, d2 up to dn is realizable. So let G be a graph that realizes that degree sequence. So that's the assumption. Here's the graph G. How many vertices does G have at this point? How many vertices? Yeah. Yeah. So let's say V1, V2, up to Vn. And V1 has degree D1, V2 has degree D2, V3 has degree D3, and Vn has degree Dn. That's the assumption. Now I've got to create a longer degree sequence. Now understand that there's a connection between this n and this k. Actually, nothing to do with, well, everything to do with the n and the k. So what do I want these degrees to go up by? What is the show that? What degree sequence do I need to show is realizable? Anybody?
Add degree k to each one again.
So I have degrees d1 through dn, and I want d1 plus k, d2 plus k, and dn plus k. Okay, so I want to add k to each of these. Okay, so let's see. Let's do that. Okay, let me add, and I don't know what this graph looks like, so I don't want to. Once you know what the graph is, you can tinker in there if you want. But at this point, I don't know what this graph looks like. So let me take k new vertices. Okay, at this point, they have no edges. That's not good because the degree sequence is v1, v2, vn, 0, 0, 0, 0, 0. Now, I want the degrees to be, I want v1 plus, I want the degree, I want a degree, a highest degree d1 plus k. Let's imagine v1 has degree d1, v2 has degree d2, vn has degree d. So what would be the easiest way to pump v1's degree up by k? Okay. Okay, so now v1 has degree d1 plus k. Now, what's the degree of this vertex here? Right now it's d2, but by this problem, I need it to be d2 plus k. How am I going to pump it up by k? and 3. Now, let's hold on for a second. What's the degree of V1?
D1 plus K.
D1 plus K. What's the degree of D2? The degree of D3.
D3 plus K.
And down to the degree of Vn. Dn plus K. What's the degree of those vertices, those K vertices, and I didn't label them. Let's imagine that those vertices are labeled W1, W2 up to WK. What's the degree of W1, the first vertex there?
N.
N. The degree of the second vertex?
N.
N. Third?
N.
And all of them have degree N. What's the degree sequence of this graph? What's the degree sequence of this graph? I'll do the easy part. How many? I got N, 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 and how many times do I have N? K times. Okay, that takes care of the vertices down here. And what are the degrees of the vertices here? So my degrees are D1 plus K, D2 plus K, D3 plus K, Dn plus K, and then N, KNs. Okay? Which is exactly what there is. Now, for some reason, I'm not going to do 10, because I probably have assigned that for homework. Okay. Oh, homework came up already, huh? Okay. Okay, so, all right, so unfortunately we've kind of run it we're through most of the class, but I want to introduce I want to introduce an important collection of graphs. Okay, so I need a couple definitions. In a graph G, so G is a graph with vertex set V, and let's just imagine edge set E. I'll suppress V of G is the vertex set of the graph G, and E of G is the edge set of G. Then S is independent in G if there are no edges between vertices in S. Okay, so the idea of independent. Okay, so I'm gonna give you a graph. Okay, here's a graph. Not very interesting. Let's call 1, 2, 3, 4, 5. The set 1, 4 of vertices is independent. Set 1, 4 is independent. The set 3, 5 is independent. The set 2, 4 is independent. Is there a set of 3 vertices where they're mutually independent? One more time. Is there a set of 3 vertices where they're mutually independent?
1, 2, 3.
1, 2. Oh, wait. 1. 1, you just told me 1, 2, 4. Just switch the order on me, and maybe I'm confused. Okay, so a subset of vertices is independent if no two vertices of S are adjacent. Okay, so let me give you. I haven't drawn the Peterson graph today. Okay, can you give me a set of 3 independent vertices? I'll label them. It's easier if I label them. 1, 2, 3, 4, 5, A, B, C, D, E. Doesn't I'm just for the heck of it. Can you give me a set? Can you give me a set of 3 independent vertices? Can you give me a set of? Can you give me a set of 2 independent vertices? Just for the heck of it. What was that? B5, 5, and 3. Okay, look at the set B, a subset of vertices, B, 5, and 3. They're mutually independent. Okay. Is there a set of 4 vertices that are mutually independent? I'm going to put B5 and 3 up here for a second. B5, 3 is independent. B5, 3. Those are independent. Means that there's no 2 of those that are adjacent. Is there one more? Can you find 4 vertices? A, B, 2, 4. Okay, A, B, 2, 4. A, B, 2, 4. You just like to see me right up here. But let's see. Could I have added C here? Okay, so I have 2 independent vertices. That's easy. I have 3 independent vertices. We found that was easy. I have 4 independent vertices. Can you find 5 independent vertices? And preferably, we'd like to not have to look at all 10 choose 5 sets of 5 vertices. That's a big number. So I'm ready to. Can you either find 5 or show me that you can't have 5? So let me point out that on the outside, I have a C5. And on the inside, although drawn differently, I also have a C5. Right? This is what's on the inside, and that's what's on the outside. Let me ask an easier question. What's the largest set of independent vertices in a C5? 2. Can you have 3? No, if I choose, you can go through the pairs, but if I choose any three, the 2 of them have to be adjacent. But this is a C5 too. You can unravel this and you get a C5. So what's the largest number of independent vertices here?
2.
And here?
2.
So the total?
4.
4. Okay, so the largest number of independent vertices. Notice I didn't even use these edges. I don't even care about these edges. Okay, so the independence number, which just for the moment I've forgotten what is he calling it mu? He's not calling it anything. Okay, we'll figure it out what he calls the independence number. But the independence number of G is the order of the largest. Let me change that. To A. Doesn't have to be the largest. There are many sets of 4 independent vertices in the Peterson graph. Can you give me a different one other than B53C? Oh, yeah. 14DC. Okay, so there are many sets of 4 independent vertices. AB24, B53C, 14CD. There's many sets of 4 independent vertices. So the independence number of G is the order of the largest independent set. In G. That's the independence number. And what we're going to, I still have 6 minutes. And what we're going to want to, we want to find the independence number for given graphs G. So we know the independence number of the Peterson graph is 4. The independence number of the Peterson. What's the independence number of a complete graph? What's the independence number of Kn? Independence number of Kn. Let me give you a Cn, Pn. Let's start with those. What's the independence number of the complete graph on n vertices?
0.
0?
0.
1.
It's complete.
It's a complete graph. Choose any vertex. Is that an independent set? Is there any edges between? Okay, well, so this is kind of vacuous. X is an independent set. There's no edges between 2 vertices. Yeah. There's no edges between 2 vertices, mainly because you don't have 2 vertices. The independence number of the complete graph is 1. What's the independence number? What is Cn? Cn. Probably it starts with a C. Cycle. Okay, cycle on n vertices. So for example, this is a C6. N divided by 2. Yep, just take every. But what about C7? Oh, so 3.5.
N minus 3.
So there's the C7. N minus 3. Do we have? So would we have 4 independent points here? I hear a yes and a no. Fight it out. If you got a 4, show me which are 4 independent vertices. See, as soon as I have my third vertex, we're in trouble. This vertex is adjacent to there, this vertex, so I can't choose anybody else. Okay, so I know the independence number of a cycle is the floor of n over 2. So the independence number there's a lot of independence number of Cn is n over 2. Oh, I didn't know we were going to have to use numbers in this. Okay, the cycle is the cycle on n vertices. What's Pn? Did I write that up there? Yeah. Oh, sorry. Back up. The easy one. The independence number of Kn, did we do that one?
Yeah.
1. Okay. Cn is n over 2 floor function. Pn? Oh, let's see. So what is Pn? A path on 3 vertices. That's P3. What's the independence number of P3? 2. P4? 2. P5? I could convince you of a lot of stuff. What's the independence number of P5? 3. Right? 1, 2, 3. P6? P7? So the independence number of Pn is, so here it's n over 2 floor function, here it's n over 2 ceiling function. Okay, one more time. Let's see, we've done the Peterson graph, we've done complete graphs, cycles, PNs. Draw your favorite graph. Draw a graph that's interesting, not your favorite one. Draw an interesting graph on 10 vertices. Now, go. You're defining what interesting means. Oh, that's an interesting graph.
I win.
I don't know. Now, once you have a graph on 10 vertices that you find appropriately interesting, find the independence number. Okay, does anybody have a graph they want to share with us? And the independence number they found? No?
Yeah.
What do you got?
I got 3 triangles.
Wait. 3 triangles? Oh, that's already interesting. 3 triangles. I'm going to draw the 3 triangles like this. Is that okay? Okay, 3 triangles.
So on their vertices, so they connect their corresponding vertices.
Okay, so, that's it. Okay, so you're going to go like this? Oh, there's an interesting graph.
Yeah.
Is that enough? Want to add some more?
Still need one vertex. So just one of these triangles just connected with another one vertex.
Okay, so you have this vertex is adjacent to these 3.
Yeah.
Okay, so that's a vertex of that's a graph on 10 vertices. What's the independence number? 3? 3?
Because each graph, they only have one independent number.
Right. Okay, so we're going to split this up. Notice that's a K4. So how many independent vertices can you have among those 4? 1. And among these 3? I should use different colors. One more time. Among these 4, among these 3, and among these 3. Because they're complete, we have one vertex, at most one vertex here, at most one vertex here, and most one vertex here. So that gives me a maximum of 3. Maximum of 3. Now I got to find 3. Can you find 3?
Yeah.
Yeah, of course. So now you know the independence number is 3. Okay? Finding the independence number is sometimes difficult. Okay, I want to. Okay, we'll start Thursday. See you Thursday.